Today we're going to look at curves that don't cooperate. So what if I give you one of my favorite functions? We learned this yesterday. What if you are given y equals x minus 1, y equals square root of x, and y equal to negative square root of x, and you are asked to find area of the region between the three curves. Actually, we'll say the three. Let's just say the three curves. So you have a little bit of a dilemma. First, you have to where is it between? What's it look like? So the first thing you always do when you have one of these questions is you need to figure out what the region between is. What is the region? And the best way to do that is to sketch a graph. So first we have to figure out or find region between curves with a sketch. This one's not as straightforward. And then after you find the region, then you have to set up an integrals or integral or integrals to find area. Okay, so favorite function and a line. This should be straightforward to graph, right? So we're just going to make a graph real fast. Well, there we go. I'm just going to take this, maybe take it. There we go. And I'm just going to move it right here, and I'm going to sketch this. All right, we're going to start with the x is equal to, or y is equal to x minus 1. We're going to graph that one first. And so it has a y-intercept of negative 1 and a slope of 1. So it's going to be a line that goes along here. And I'm going to make a line. And I'm going to go through the 2 points. There we go. There's the one line. And then the next one, actually we're going to change this. We're going to move this so we can exaggerate the curves a little bit, because otherwise it's kind of hard to see. So I'm just going to move this down. We'll pretend that that's one there, so that it's a little easier to see. Oops, didn't mean to do that. Undo. Let's erase this one. We won't worry about that other one. We'll get it later. Or actually, I bet I can get it if I... do it again. There we go. All right. So we're going to exaggerate it a bit. We're going to say that that's 1. So up here on this scale, we'll say that that's 1. So that's 1, 1 is what we're going to say. We'll say that's 1, 1. All right. And this is 1, negative 1. And if we're graphing, so let's label this. This is y equal to x minus 1. This is y equal to square root of x. And this is y equal to negative square root of x. And it's not perfect, but it's good enough for our purposes. It's clear to see that the two square roots intersect at 0, 0, right? So that's one point of intersection right there. That's pretty easy to spot. And it's easy to see that the curves are going to intersect somewhere down here. And it may not be pretty, but that's okay. We'll worry about that in a second. And they're also going to intersect somewhere up here. So what we have to do is we need to find this point of intersection and this point of intersection. They may not be pretty for this particular example. I didn't set this up to be as nice as some of the ones I set up, but I just want to show you for example. We're going to find those points of intersection by setting the pieces equal to each other, right? So we're going to go, okay, well, that means that for this one over here, we have so we'll call this A. We know what that one is. That's 0, 0. That's A. This is B, and then we'll say this is the C value. So we had 3 x values where we're having intersections. And we would set them equal to each other. We're just going to find them later, all right? But for now, we look at this and we go, okay, well, that's great. We can find these points of intersections. I just want to show you, if I come up from B right here, right there, we have a dilemma on either side of B. If we're to the left of it, do you see that all of the cross sections right here in this region, the upper curve is the square root of x and the lower curve is the negative square root of x. But if we go on the other side go to the right of B, over here we have a different problem. Here the square root of x is above x minus 1. So we have different upper and lower curves. That's going to present a problem because when we go to integrate, we're going to have to integrate from A to B with one set of conditions and from B to C with a different set of conditions. So if we're just looking at this generically, if we were to set this up and we want to find this region right here, we're going to set up a bunch of cross sections going from B to C. And then for the other one, we're going to go a bunch of cross sections from A to B. So when we go to find this, we've got a length here, this length right here. That length is going to be the upper curve is square root of x, and the lower curve is the x minus 1. So that's length 2. And over here, this length, we'll call this length 1. Length 1 is equal to the upper curve is the square root of x, and the lower curve is, so we're doing minus negative square root of x. When we simplify that, L1 is equal to 2 square root of x's. And over here, L2 is equal to square root of x minus x plus 1. It's not pretty, but we can do it. And so if we were to go and write the area for this, we would write it as the area is equal to the integral from A to B of the first length, which is 2 square root of x dx, plus the integral from B to C of the second length, which is 2 square root of x dx. And we could do it if we had to. We would have to form, the points of intersections aren't going to be nice, but we could figure them out. But this seems very awkward and a little more difficult than it should be. And in fact, there are many problems where doing cross-sections, vertical cross-sections, does not help you. You need to do horizontal cross-sections. But to do horizontal cross-sections, we can't have everything solved for y and with respect to x. We have to flip it around and do solving for x so that it's with respect to y. So remember when we were doing implicit differentiation, we could take the derivative with respect to different variables. We can do the same thing when we're doing integration. And what you're going to see is that for this one, taking the integrals and doing cross-sections with respect to x do not make this problem easy. In fact, they make it difficult. So let's take another approach. if we look at this, could we rewrite this whole problem in terms of y? So let me go in here. I need to change my paper size to letter real quick so it makes it a little easier. Actually, yeah, T. Come on. Okay, it's not working, so I'm not going to worry about it. All right. We could take a different approach. So let's look at these functions. Let's put it together a little different way. If we switch this around, and instead of doing everything in terms of x, we solve for y. Let me just add another page, and I'll change the title in a little minute. We're going to change everything in terms of x. So our original equation was y equal to x minus 1. We're going to solve for x, and in this case it becomes x equals y plus 1. We had y equals to square root of x. If we square both sides, this is going to give us y squared is equal to x. And that is actually true for both y equal to x and y equal to negative x, or negative square root of x. They both give you the same thing. Because if you remember back to parabolas when you were in Algebra 2, when you have a sideways parabola like that, it covers both of the square root and the negative square root. So let me show you what the graph looks like. If we switch it around, now what we're doing is we have everything in terms of y. Before, for this one, for our first one, let me go, maybe it'll let me go back. Maybe it won't let me go back. It's not liking this. Okay, we're just going to stay here. I'll go back in a minute. But so for this one, we're doing everything in terms of y this time. So instead of 3 curves, we have 2 curves to create the region. We have one curve is the x equal to y plus 1, and our second curve is x equal to y squared. It'll give us the same thing. So we go and we get an axis. And we're going to sketch in x equal to y plus 1, which is the same as y equal x plus 1. So we're going to say this is negative 1 down here, just for giggles. And then we're going to put a line through it. And then, oops, it shifted. There we go. And come on. Then what we do is we're going to graph the x equal y squared. Well, that's 0 here. And then at 1, which is 1, 1, and negative 1, 1. About there. And so when we sketch it, we now have 2 curves instead of 3. But remember how when we were doing cross sections, we did them vertically? If we're going to do everything with respect to y, that means our cross sections have to be horizontal, because we want all of our little rectangles, we want to look at them and we want to see that this is delta y. If we look on the end, that's delta y. And this length in here, this length right there, we just take that length. That length is actually, I need to get a pen, not a highlighter. That length right there, that length is right minus left. Because if you always subtract a right number minus the left number, you get a positive number. Remember how we did upper minus lower? Now we're going to do right minus left. And if you look at this, you realize that if we always do right minus left, we don't have to change what's right and what's left. We can do the whole region just doing right minus left. And now we're going to have points of intersection. We have one point of intersection right here. We're going to call this C. And another one up here we're going to call D. And if we're going to fill this, we're going to fill it in. We're going to go from lowest to highest. Remember last time we integrate from left to right? Well, we will integrate from bottom to top too. So we're going to fill this thing with rectangles that are infinitely thin on the y dimension. And they're going to go from C to D. Whereas when we do vertical, they're going from A to B. Now they're going C to D. It's the same concept. So we just need one area. One region for the area. One integral is going to be the integral from C to D of right minus left. Well, our rightmost is the y plus 1. Our xmost is the y squared. And now we just have to integrate one integral, and it's a really simple one. We got rid of the square roots. So what you're going to find is there are times when it is much easier to do right minus left and integrate from lowest to highest instead of doing highest minus lowest or upper minus lower, integrating from left to right. And we'll go over an example where it has nice intersections and we can actually do it in class. So that's it for this video.